In order to properly design a Bloom filter, we need to first figure out what's the probability of encountering a false positive in my Bloom filter. So to derive this probability, we're going to make two simplifying assumptions. First, we're going to assume that each of our k hash functions uniformly distributes across the array. In other words, for any of your hash functions, the probability that it'll send an element into any of these m bits should be uniform. It should be exactly 1 over m probability to hit any of these bits. And the second simplifying assumption is that each of our n insertions is independent. The first element that I insert should be completely independent from the second element that I insert. They should all just kind of be random elements. Okay, so let's derive this probability of having a false positive. So the probability of setting a specific bit to true from a single hash function of a single insertion is 1 over m by my simplifying assumption number 1. For a single hash function in one insertion, I have 1 over m chance of hitting any of these m bits. Therefore, the probability that a specific bit happens to not be set true by this insertion is m minus 1 over m. This is the probability that a specific bit is not set true after one hash function of one insertion. Why? It's because we selected any of the other m minus 1 bits instead. So if I have k independent hash functions, if this is the probability of this single bit being not set to true after one hash function, the probability of this bit not being set to true by any of my k hash functions would just be this multiplied by itself k times, because it's independent, which is just this quantity to the power of k. We're going to use a well-known identity that the limit as m approaches infinity of the quantity m minus 1 over m to the m is just 1 over e, or in other words, e to the negative 1. So this is an identity that I'm not going to derive. This is just an identity in math. So using this, I can actually rewrite this statement. I can rewrite this as m minus 1 over m raised to the power of m, that entire quantity raised to the power of k over m, right? Because m times k over m is just k. So these two are equal. But now I can use this limit to equate this to basically inside of here would just be e to the negative 1. So this would yield e to the negative k over m, specifically as m approaches infinity. So for sufficiently large values of m, we would get e to the negative k over m. Again, I'm just plugging in e to the negative 1 for this exact quantity. So as m is sufficiently large, we would get this, I guess I'll say squiggly, it tends to be close to this value, assuming large values of m. Okay, so this is now the probability that after k hash functions of one insertion, this specific bit was not set to true. It remained false. So if I have n independent insertions, the probability of this bit not being set to true by any of those k hash functions, this is from one insertion, but during any of my n insertions, well, if this is for one insertion and each insertion is independent, the probability that it's not set to true after n insertions is just this times itself n times, or in other words, I could just raise this to the power of n. So this is e to the negative kn over m. So this is the probability that after n insertions, with each of these k hash functions, this is the probability that a specific bit was not set to true. So the probability that the specific bit is set to true after all of those insertions, after all of those hash functions, is just 1 minus this. So the probability that a given bit was set to true after k hash functions with n independent insertions is 1 minus e to the negative kn over m. So given that a single new element that I'm searching for does not exist in my Bloom filter, the probability of a false positive, so each of my k hash functions happens to go to an index that is set to true. So let me just reiterate. This is the probability that a specific bit is set to true after k hash functions with n insertions. So given a new element that truly does not exist in my Bloom filter, the probability of a false positive, in other words, the probability that each of my k hash functions happen to go to an index that is already set to true, is this probability raised to the power of k for each of my k different hash functions. So this is just, so the probability of a false positive, which I'm going to write using epsilon, that's my symbol, it's roughly equal to this quantity that I came. This was for a single bit, so negative kn over m raised to the k power. So this is the probability of a false positive. And the reason why I say approximately equal to is because I made this approximation here. So given sufficiently large values of m, this false positive, the probability of a false positive is well estimated by this equation. So now that I've derived the probability of a false positive as a function of n, m, and k, I can use this to design an optimal Bloom filter. Now that I've derived the probability of a false positive in a Bloom filter, I can use this information to design an optimal Bloom filter for my purposes. So remember, this was the equation that I derived. The probability of a false positive, which I'm denoting as epsilon, is roughly equivalent to 1 minus e to the negative kn over m, quantity raised to the power of k. And remember, this is approximate because this is the limit as m approaches infinity. So for sufficiently large values of m, this is a good estimator of the probability of a false positive. Just looking at this, so I know I can't have false negatives, I only care about false positives, and I specifically want to minimize the probability of a false positive. So how do I minimize this? Well, I, as the designer, have no control over n. The user is the person that dictates the value of n, the number of elements. But I do have power over k and m, so I should design optimal k and m. If we look at this, just looking at this probability, if we have bigger m, so more bits, we have a lower probability of having false positives. So with respect to m, we have to find this kind of sweet spot of big enough to minimize the false positive probability to be a sufficiently small value, but not so big that we're wasting too much space. So given n and m, we can basically minimize this function just using regular calculus. We can minimize this function, and the value of k that minimizes it is k equals m over n natural log of 2. So m over n times the natural log of 2. And similarly, I can find that m equals negative n times the natural log of my false positive probability divided by the natural log of 2 quantity squared. So I can use this to actually define I can define k as a function of the probability of false positives. So k would actually be equal to negative log base 2 of the false positive probability. So k only depends on my desired probability of false positives. And remember, k must be an integer, so I would actually take the ceiling of this equation. Whatever this gives me, I would want to go up to the nearest larger integer. And then, as mentioned, this is how I can find m. Okay, so given these two equations, how can I design an optimal Bloom filter? It's actually not too bad. So first, I need to estimate n. And as the developer, I don't know exactly what n would be necessarily. I can hopefully guess, or maybe have the user give me a guess of, is it 1,000, 100,000, some order of magnitude ballpark. I can overestimate if I'm unsure. So roughly guess what is the size of n. Then I can also pick the false positive probability. So pick a probability of false positives that is appropriate for my purposes. So remember, the bigger this value is, the less accurate. The smaller this value is, the more accurate my Bloom filter, so the less false positives, but also more memory consumption. So the smaller I make this value, the less false positives, but the more memory that I use. So just pick this value and estimate this value. Now that I have n and epsilon, I can find the number of hash functions that I need to use. K equals negative log base 2 of the probability of false positives that the user specified. And then I can pick m using this equation. M equals negative n times the natural log of my false positive probability divided by the natural log of 2 quantity squared. So pick that, pick that.